Okay, so in this presentation we're going to have a look at SHA-3 and Keccak. So SHA-3 is associated with hashing methods, but we'll see that it can do a whole lot more than that. So with hashing methods, what we typically do is we take a whole lot of data and then produce a standard fixed sized hash. So that started really with MD5. There was other ones before this, but MD5 was one of the most widely used, and it produced a 128-bit hash. Unfortunately, it's not too difficult to create collisions. Even where we take different images, it's possible for us to stuff bytes into the images and produce the same MD5 signature. The same thing can happen for executable programs, where we can have a different program that can have the same MD5 signature. So that was advanced on to SHA-1, which produces a 160-bit hash. So there are a vastly increased size, 2 to the power of 160 different hashes here. So it's a lot more difficult to create a collision. Unfortunately, it was shown by Google that it was possible to take 2 PDF documents and create the same SHA-1 signature for them. It took about a year and a half on our distributed computing architecture for that to happen, but it showed the possibility that SHA-1 could create collisions. So for many systems, SHA-1 has now been deprecated, and we won't really find any certificates that are signed by SHA-1 on the internet. SHA-2 improves things and is much more secure. So it's a new method, and it's a different method from SHA-1, and we can get 224, 256-bit, 384 and 512-bit hash signatures with SHA-2. This is fairly secure because we vastly increase the number of bits that we have here, and especially for 256 and 512, it is highly secure. But there was a worry that this method could be broken. There might be a weakness in there, and certainly the way that we had evolved these signatures, NIST decided that they wanted to they created a competition to define the next generation of hash signatures. So the short list was the Keccak, Blake, Grost, Skeen and JH. And we'll see the performance of these in a little minute. And it was announced on October 2012 that the winner was this one here that we're going to have a look at. So SHA-3 has since been standardized for 224-bit, 256, 384 and 512-bit. These produce fixed length hash signatures in the same way that these different methods produced it. So that's quite useful for things like file hash signatures and for data. But there's a whole lot more in the method. It's a sponge method that this method uses, and there's a whole lot more things that we can use this for, and for that we can actually define a method called SHAKE, which is based on this Keccak method, and we can produce 128-bit and 256-bit, but to give us any length of output here. With this, we can actually break away from using these methods as hash methods and start to use it for things like symmetric key encryption and for signing as we would with the public key. So we'll have a look at both the SHA-3 and SHAKE and see how they're actually used. But it really was a major advancement, and it created what's called a sponge construction. Okay, so let's have a look at what the assessment was that NIST performed. So the tests were performed within a set number of organizations, to be fair, and we can see here that in terms of the area, in terms of the gate, the gate equivalence, that's really relating to the size of the implementation and hardware. This method did very well. SHA-2 does well here, and Blake itself did very well. So Blake probably won this section here. Unfortunately, at the time, it didn't win, but Blake2 has came along, and that's vastly improved its performance. But you can see these methods here struggled a little bit for the size of the area that the implementation took up. Where Keccak really took off was in the throughput per area. You can see here it performed very well, often 2 or 3 times faster than the other hashing methods. The original Blake struggled here, but now a new Blake2 has been released, and it can now compete with this performance here. But the other ones didn't do too well here, so in this case Keccak won. And then in the amount of energy, so it's really important for IoT devices that they don't drain too much power. And that, again, this is where our Keccak stood out, and Blake, you can see, was more power hungry, and this one here was the most hungry of all, along with this scheme. So NIST elected this method, Keccak, as the winner for SHA-3. So let's look at how it all works. Okay, so if you think about AES has a block size of 128, so it has basically a state size of 128 bits. If we use 128-bit keys, it's 10 rounds, 12 rounds for 192, and 14 rounds for 256-bit AES. Keccak is different, and it's more powerful. It has a state size of 1600 bits. That's a massive number of states that we can actually have. 2 to the power of 1600 is a lot of, it's a very large number. And what we do is we define a variable called L, and we say it's 25. So we have 5 by 5, our little block size for our state, and then we can have multiple dimensions of that. So if we go for 1, 2, 3, 4, 5, and then 6. So for 6, we get 1600 bits. This is fairly secure, and this is ultra secure. So it's likely to last for 30, 40 years at least for the security level. So 16 bits is often chosen. This value of L is 6. The number of rounds that we use is 12 times 2 L. L is 6. So we go for 24 rounds. I'll explain how the rounds come in a little minute. So for the standard, for the state, we have a value called a rate value and a value called the capacity value. This value plus this value equals 1600, and we split them up. The rate we'll use to exclusive OR with the message, and the capacity is then used to be able to merge in with a function, and we'll see how that works in a little minute. So the outputs are fixed here for these SHA methods. Related to this should be 256, related to the output size required. But for SHAKE, we're using the same method, but we end up with any length of output. We could ask for 1 byte or 1 billion bytes. It's up to us to define the output of SHAKE. So this gives us a lot more flexibility in the output that we get. So the value of the rate is predefined. So we have 1152 bits for 224 and 448 bits here. For SHA-3 512, we have 576 bits here and 1024 bits there. But always we end up with a state which is 1600 bits long. Okay, it's really important. So it's often defined as Keccak 1600 because we're using 1600 bits for every state that we have. Okay. So what we do is that we take the message and we will pad related to the number of bits that we need for R, so that we can get a multiple of this value. So in this case, if we are going for SHA-3 224, the R value would be 1152. The C value is 448. So we'll take our first part of the data as 1152 here, and then any bits that we've got, any other bits that we've got, maybe we're looking at a large file, we would chunk it up into 1152 bit chunks and then would pad at the end. So the number of times we go in here will relate to the number of these chunks that we're actually creating for our message. So let's take the first one. So we take all zeros and all zeros here, and then we feed it into an exclusive OR function. Very simple. So we'll take 1152 zeros and exclusive OR it with the message coming in. So we take 1152 bits of zeros, and we'll take the first 1152 bits and XOR them together to give us this output here. We then put it into a function which has exclusive OR gates, NOTs, and functions in here, and do some sort of logic for 24 rounds, and then we output here. This becomes our first state. Okay, so if I rewind, we take 1152 bits for SHA-3 224, and we take our message, XOR that with the 1152 bits, and it goes into here. We have 24 rounds of doing these XOR and type functions in here, and we'll end up with an output here. This will also be 1152, and this will be 448 in terms of SHA-224. This is our first state output. Then if we have more bits left, then we'll take the next 1152 bits if it's SHA-224, and we'll take the current state and we'll XOR that. That's 1152 bits, XOR that with the 1152 bits here, and we'll get an output there. We then take the capacity, and that then goes into the 24 rounds again of this function, and then we get the next state here. This phase is called the absorbing phase because it's a bit like a sponge where it's absorbing all of the message and defining the states that it has. Once we've finished the absorption, so we'll go through that for ever number of times for the amount of data that we have. So in this case, it's just 2 times. So we end up here. So this is the state at the end of moving through the absorption phase. Once we've finished and we don't have any more data, then we will go into a squeezing phase where we squeeze the bits out. And this is fairly simple. We just go put our state into the first round, and then on the output will be 1152 bits. We only need 224 bits, so we just take the first 224 bits and then that becomes our hash there. If we need a bigger one, such as with SHAKE, we might go through several of these functions to create the state. But in most cases here, then we'll go through one, and maybe for the even for the 512-bit version, we'll have 576 rate bits here. So we'll just take the first 512 bits, and that becomes our hash. Okay, so if you follow through what we did, we took all our data, we chopped it into the size of the rate, we excluded for, we put it into the functions, that becomes our state. We then feed the next part of the data in, and then we chain until we get to the end of our data. We then go to the squeezing function, into the same function again, 24 rounds, and then we get our output there. If we need more, then we will go through this again and again and again until we get our output. So it's within SHAKE that we can have multiple outputs. So if we need more data going out, then we will go through that function several times. Okay, so this is what this is how it's represented from there. So there's the functions. That's the message going through and XORing in with the R value. There's initialization of the 0. This is the function here with the 24 rounds, and so on. So the more data that we have, the more times that we'll have to go through these rounds, because we'll have to fit in with little R blocks of chunks. At the end, we go through multiple, or we could go through one or more of these stages, and then that will give us our output there. Okay, so let's have a look at some examples. So we'll look at first at SHA-3. So this is a little Python program here. I've taken some test vectors and tried it out, and we're just importing SHA-3, and then we just take our hash function lib, just update it, and then we'll take our digest. So these are the test vectors that we've got. So if we take ABC, we should get ABC. For SHA-224, we should get E64. E64 is correct. Okay, so that's for SHA-3, and that produces a fixed length. There is a slightly different standard for it that we can use for this one here, and then also for SHAKE. Yeah. And we'll look at this. We'll just look at the Keccak function on its own. So in this case, I've used Go to be able to implement this. So this is the SHA-3 function here, and this is our SHAKE method here for 128-bit and for 256-bit. So with this now, what we can do is we can have various lengths of our output. So there is 64 bytes, which is 512 bits. And we can see here for our input, we can create virtually any size of output that we have. And it's what's called an extendable output function, where we can vary the output, and it doesn't just produce a fixed length signature. So the original version was submitted, and it had reasonable performance, but since Blake2 was released, it managed to perform significantly better than the original specification. So the Keccak team have since worked on it and reduced the rounds down to 12. So with inside these functions, there is only 12 rounds. So that significantly reduces the time that is required for processing. And this is an example here of the Kangaroo12 method. That's in there. And with this, we get what's called a custom string. So we can actually add an initializer into the method and produce our output dependent on that and the data payload. This allows us to apply things like symmetric key encryption into the method. So again, we can use this. There's a customization string, and we're just producing a fixed length output here. So the performance of Kangaroo12 is significantly better than even Blake. So Blake beat SHAKE 1 to 8. This is the cycles per byte. And you can see here Blake2 is significantly faster than SHAKE, and also MD5, SHA-256, and so on. And generally performed better. We can see some of the other ones really struggle around here. But Kangaroo12 is one of the fastest hashing methods around just now. Okay, so that's been an outline of SHA-3 and Keccak.